composition of compounds. The chemical formula and the molar masses give us the relative quantities of each element, and that can be very, very useful information, very practical information. So we'll sometimes talk about the percent composition or the mass percent composition of an element in a compound. In general, percent means the part that we're interested in divided by the whole thing times 100. The part and the whole are often measured in the same unit, and so the units cancel out. If we're measuring in grams, it might be the mass of iron in grams in the whole compound measured in grams. We can determine mass percent of each element two different ways. We can calculate it from the formula of the compound. If we know what the formula is, we can calculate it. Or we can determine it experimentally if we don't know what the compound is. In theory, the percentage of each element, when you add the different elements together, in theory, it should add up to 100%. Occasionally, it's off by a little bit due to rounding and errors in measuring. The general equation is the mass percent of element X, whichever one we're interested in, the mass of element X in 1 mole of the compound divided by the mass of the whole compound times 100 to make it a percentage. Acetic acid, C2H4O2, is the active ingredient in vinegar. That's what gives it that distinctive vinegar smell. Calculate the mass percent composition of oxygen in acetic acid. So we're going to calculate the percent of oxygen from the chemical formula. Percent oxygen is going to equal the grams of oxygen divided by the grams of the whole thing times 100. They didn't give us the mass, though, did they? If they gave us the two masses, you just plug them in and we'd be done. They didn't give us any masses. Percent composition is one of those intensive properties that does not depend on how much there is. It's always the same. So what we can do is we just choose an amount that we think is convenient. It's very convenient to choose 1 mole. So I'm going to choose 1 mole, and I can calculate the mass of 1 mole. We just learned how to do that. And then I can look at this formula and figure out how many moles of oxygen there are, and I can figure out how much mass of oxygen there is. So we're just going to choose 1 mole. Well, what's the mass of 1 mole of acetic acid? It's just the molar mass, right? So we've got 2 times the mass of carbon plus 4 times the mass of hydrogen and 2 times the mass of oxygen. Two times 12.01 plus 4 times 1.008 plus 2 times 16. 60.052 grams. And I'll have 2 decimal places. So in our percent composition formula, that's the mass of 1 mole of the whole compound, 60 grams. What's the mass of oxygen? 32. All we have to do is pick out the oxygen from what we wrote down. This is the mass of the oxygen. Because there are 2 moles of oxygen in every mole of this compound. So 32. Times 100. So we have 32 divided by 60.052 times 100. Yeah, 53.1 4 sig figs, 0.29%. That's the percent of oxygen. Any questions? Yes?
When, like for example, the periodic table here is more than the 4 significant figures, so using those numbers, we got 53.28. Is that going to be something we get to?
That's a good question. So he used more precise values, and he got 53.28%. That can happen depending on which periodic table you're using, if you've got more or fewer sig figs. That is a small difference in the last significant figure where there's uncertainty anyway. And so that's fine. It's not going to be a problem. Good question. Yes?
So if it was going to be like C2H4O3, it would be just oxygen times 3?
Yes.
Okay.
So if the formula here had O3, then this would be 3 times 16 in the numerator. It would also change the denominator a little bit. Any other questions? Mass percent works really nicely as a conversion factor. It relates mass of the element to mass of the compound. Here, what we need to remember is that percent means per 100, literally per 100. So here's an example. Freon 112, which is C2Cl4F2, is 69.58% chlorine by mass. This percent means 69.58 grams of chlorine per 100 grams of the compound. If you did the online homework, you came across a very puzzling problem involving lead and galena ore and these percentages and efficiency, and a lot of you went, what? Yeah, that was supposed to kind of push you and make you uncomfortable. Any percentage can be treated like this. So 69.58% chlorine. That means 69.58 grams per 100 grams of the whole thing. If we go back to this acetic acid example, this means there are 53.29 grams of oxygen per 100 grams of acetic acid. So that can save us some steps in calculations. Let's do an example. What mass in grams of iron 3 oxide contains 58.7 grams of iron? Well, we can solve that using molar mass and moles in the formula, but here they're giving us this nice percentage. Iron 3 oxide is 69.94% iron by mass. So let's write down the numbers that we were given. 58.7 grams of iron and 69.94% iron by mass. So that's 69.94 grams of iron per 100 grams of iron 3 oxide. Now you wouldn't have to write the formula here, but I'm just going to do it anyway. You could write the name, that would work too. What are they asking me to find? Grams of iron oxide. So I've got grams of iron oxide over here. And I'm starting with one of these numbers. Which one do I want to start with? The 58.7 grams. This cannot be used as a conversion factor. This looks like an awesome conversion factor. This has per units, this per that. So I'm going to start with this. This conversion factor allows me to do this in one step. And the units are going to assist me. So 58.7 grams of iron. One arrow, one conversion factor. Grams of the iron oxide is the other numerator unit. And then grams of iron comes down here. So that grams of iron cancel out. We're getting to that point now where we need to specify grams of what. If you just put grams in, it's easy to get things all twisted up. Grams of iron are not the same as grams of iron 3 oxide. Now we look at this conversion factor that we made from the percentage. And the 69.94 is with the iron. And so I'm going to put that in the denominator with the correct unit. And the 100 grams goes in the numerator. This 100 can be considered an exact number. The 69.94 is the measured number. 69.94 plus or minus 0.01 grams in exactly 100 grams of the mass. So this is not going to limit anything. The number on top is going to do that. So 58.7 times 100 divided by 69.94. How many significant figures would this answer have? 3. So 83.9 grams of Fe2O3. Questions? This is not the only way you can solve this problem using a percentage. Question?
I did it, I divided 58.7 by 69.94 and then multiplied it by, and I got 60.
That would work as well. He took this 58.7 divided by the 69 and then multiplied by 100. That'll get you the same thing. Some of you are good with percentages, and you can say, oh, well, you know, I just do it. That's okay with percentages. Just be careful. Any other questions? So we can use mass percent as a conversion factor. We can also get conversion factors directly from the chemical formulas. They have these inherent relationships between numbers of atoms and molecules. So this Freon, C2Cl4F2. The formula tells that there's 2 moles of carbon. There's 2 moles of carbon for 1 mole of the entire compound. We could make another one. There's 4 moles of chlorine per 1 mole. How many moles of fluorine per 1 mole of the compound? 2. What's important to remember is that these give us relationships in moles and not in grams. Okay? This is moles of carbon to moles of compound, not grams to grams. The percent gives us grams. These chemical formulas give us moles. Determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. And here we're using chemical formulas as conversion factors. You notice they didn't give us the percent composition. If they give you percent, go ahead and use it. It's faster. But what if you don't have that? You could calculate it from the formula, but that's going to take just as much time as using the formula as a conversion factor. So we'll just go ahead and use it. What's one thing we have to figure out before we can start this problem? We need the molar mass of aluminum sulfate, but before we can do that, we need the formula. What kind of a compound is aluminum sulfate? It's ionic because it starts with aluminum. So to find the formula, we have to write the formulas for the individual ions. So we've got aluminum. What's the charge on aluminum ion? 3 plus. What's the formula for sulfate? SO4, 2 minus. So then we have to put those 2 together. We're going to need 2 aluminums and 3 sulfate ions. And if you need help with that part, please come see me individually. So we have 7.2 grams of aluminum sulfate. And what do they want us to find? Mass of oxygen, or grams of oxygen. How are we going to get from mass of the compound to mass of one of the elements? We're going to need to use the mole ratio, right? When we look at this formula, in one of these, how many oxygen are there? 12, right? So 1 mole of aluminum sulfate contains 12 moles of oxygen. So if we had moles of aluminum sulfate in here, whoops, we could convert to moles of oxygen. Can we go from moles of oxygen to grams of oxygen? Sure we can. Can we go from grams of aluminum sulfate to moles of aluminum sulfate? Sure we can. If you're trying to convert from one thing to another thing, another substance, mole is often going to show up in the middle of those conversions. 7.2 grams of aluminum sulfate. I completely understand that it gets tedious to write all these formulas. Do you think I'm enjoying writing these formulas right now? I am not. It's important though, because otherwise you come up with the wrong answer, and that's even more tedious. And next is moles of oxygen, and finally is grams of oxygen. The path tells me what units to put on the top. And I put units in the bottom so that the units cancel out and leave me what I want left. Those guys cancel. And then I've got grams of aluminum sulfate down here. I like to do the easy one first. I think this one in the middle is the easiest. So you get it directly from the formula. We wrote it out here though. 1 mole of the compound contains 12 moles of oxygen. So there's 12 moles of oxygen for every 1 mole of compound. The last one is pretty easy too, because we're talking grams of oxygen and moles of oxygen. We just look at the periodic table. 16. This one we're going to have to calculate. So we've got 2 times the mass of aluminum. I'm going with the one in my head. How many sulfurs? 3. 3 times the mass of sulfur, and 12 oxygens. Two times 26.98 plus 3 times 32.07 plus 12 times 16 equals 342.17 grams equals 1 mole. Okay, so now I've got 342.17 in there. Now I just go across, left to right, multiply and divide. 7.2 divided by 342.17 times 12 times 16. 2 sig figs on this answer, 4.0 grams of oxygen. Any questions? It was kind of a long process. Would this be more difficult if we didn't know how to do dimensional analysis? Yeah. We're going to have a lot of calculations like this, where there's 3 terms, and we've got moles of this and moles of that, and grams in there. And if you haven't gotten the hang of dimensional analysis yet, it's not too late. It's going to be very, very useful still. This part we're going to save for next time.